All right, seems like we could get started. So thanks for joining one more time. This is our first Munch and Learn for 2022. And I'm pleased to, I'm Didier Lally, I'm part of the HPE Dev team, and we'll be hosting this talk on location. Location matters, and learn how to succeed at the edge with HPE Ezmeral and NVIDIA. So we have three speakers today, Matt, William, and Denis. They will be taking over after a quick introduction from me on the HPE Dev activities. As I said, this is our first Munch and Learn for 22. We had 11 talks last year. We hope to get 12 talks this year on a monthly basis. We have a calendar for those events on this webpage here. You can find not only the next upcoming sessions and registration links, but also you can find the replay on our YouTube channel for all of the past sessions. We have two more sessions shaping up, one in February with Neil Conway, who's the VP of Engineering and Artificial Intelligence and High Performance Computing at HPE, previously with Determine AI, which HPE acquired. The session will be about the golden age of AI and the dark ages of AI infrastructure. That sounds like an interesting thing that we don't want to miss. So February 16 is the date. Don't miss that one. Don't try to register because I didn't put up the link yet, but I'll do that today for sure. And next will be in March, and we have a session on zero trust and how to build a robust identity into Istio using Spire. So we are changing gear a little bit, but very interesting session here, end of March 23rd, sorry. We also introduced a new type of talk for this year. We call this meetups. And what they are is really meetups in the open source kind of way we know it. So there will be in-depth on a given technology, more on sometimes a product or project. We already have a session planned for January 26. We have a page with all these links available for registration. Again, this is open to everyone. The first session will be on Quarkus, presented by an engineer from Red Hat. The second session in February will be on Streamlight, presented by an engineer from Streamlight. We have those two confirmed. We have two more coming up on vFunction and another one on Open Policy Agent from company Stira. And these two are yet to be confirmed, but should be good. So I'll update the calendar page for the meetups, but think about that when doing open source and wanted to learn more about some specific technologies. As always, these are called Munch and Learn because, you know, people are joining from all over the world. So they might be at dinner, they might be at breakfast, and we'd be happy to see what they're having for munch. And we have a Slack workspace that you can join to share your munchies with us, or you can also use our Twitter and post there if you want. And we'd be happy to see those pictures. That's for fun. With that, I'll just remind you that we have a fair amount of channels that we communicate to. If you want to know about all the links that I talked about, you can scan that QR code and get all the links from our community page. And otherwise, everything starts at hpedev.io. So please mark this down. With that, I'd like to hand over to Matt for the rest of this wonderful session. Thank you very much.
Great, thanks, Didier. I think we're going to switch over, and Denis is going to put a presentation up here as I get started here. But welcome, everyone. I'm really excited to be able to host this session on location. So I've been in the data analytics space for a long time now, and you know, the idea of edge and just edge intelligence and distributed analytics has really been a future-looking thing. As I look back to my days at Teradata and Oracle's and in the big data time, it was all kind of future looking. It was kind of nice to have, hey, our IoT devices are going to enable X, Y, and Z in the future. But we are still stuck in that mindset of business analytics and the data warehouse or data center out or your public cloud out kind of concept. And really what we've seen is technologies and capabilities have really evolved very quickly over the last decade to really enabling that true edge to multi-cloud existence. So what we're going to be talking about today here, I'm joined by Denis Vilfort and Will Benton from HPE and NVIDIA respectively. We're going to talk through kind of the shifts that have happened that are allowing this kind of edge in as opposed to data center out or cloud out kind of architecture to happen, and why it's so important to think about, from where your data is actually generating and coming from the edge to think from an edge in perspective. So like I said, I'm joined by Denis and Will today. So they're going to be going through kind of the background and the technologies to enable these type of architectures. We're going to go through a couple of examples on how we can deliver this, for your more modern distributed solutions. And last but not least is we're leaving a bunch of time at the end for Q&A. So if you do have some questions throughout, if you want to put them into the chat, I'll see if I can have Denis or Will address them as they're speaking in their sections, or we can hit them at the end, kind of at the round table. So with that, I want to turn this over to Denis to kick us off. Denis, over to you. Thank you.
Thank you, Matt. Appreciate it. And it's an honor to be here with you guys on the first one of the new 2022. So let's talk a little bit about that. What's going on? Well, technology moves in waves, and we all know the data center yesteryear, right? Which is really an outcropping of mainframe thinking from back in the old IBM mainframe days. And then, as you all know, people sort of around like 10, 15 years ago started getting antsy that, you know what? I don't really want to be, I'm manufacturing candy bars, let's say. I don't want to be in the IT business. I want to be in the candy business. So they decided that maybe they needed some help, and they would go to a cloud provider that will then run their centralized construct, which was still, but just the data center, but it was run by somebody else. And this is important to understand because we used to call it data center. It was a centralized way of thinking. And you start saying, okay, that's all this good with the world. We understand those two paradigms. Either somebody else manages it for me, or I used to manage it, and it's still the same. Now what's happening is we're actually seeing a third wave. And the third wave is actually edge computing. What does that mean? Well, I want to say it's not just about compute. A lot of people think, oh, that means edge compute. No, it's about moving everything, software, sensors, networking, everything out to where the company is actually conducting business. And I can tell you, we're working with some of the biggest, obviously HPE, and we've had companies coming to us saying, listen, we have 360 worldwide company locations, some of them in China, and we can't manage all of this. We need help. So now we need the cloud that comes to you, and that's actually edge computing. Still a cloud experience, but it's sort of distributed as opposed to concentrated. So when you look at that, you can start saying, well, why on earth do we need to go through this? Well, it really has to do with where the data is. Oh, there's a double D there and deployed, I saw, little typo. All right, so check this out. The data is being generated in the 360 locations worldwide, or if you're a Starbucks, we're talking about the coffee being made in 34,000 stores worldwide. So the data is where the activity takes place. Think of a hospital. That needs to be where the patients are, right? So if the hospital needs where the patients are, guess what? We can't just have one central hospital in Chicago. We have to have a distributed enterprise. So if the data is actually out there, what is the problem with cloud computing, or any centralized computing for that matter? And that is, there's time lost in moving the data for central processing. Now, this is like in Dickens' time, you used to send out the roast or the turkey to be baked by the baker because he was the only one who had an oven big enough. Nobody does that today. Why? Because we've democratized ovens. Everybody has an oven in their home big enough to cook a turkey. So this is exactly what's happening with compute. Data centers are shrinking and they're moving to the edge. So the concept that's now happening is, why don't we distribute the compute? We can still have cloud computing for centralized functions, but we now have augmented that with a decentralized edge computing strategy. Okay, so you get that. Not surprisingly, the analysts are picking up on this, right? And they're saying, hey, we're going to have 55 billion devices creating data all over the place this year. And already 50% moving to 73% of the data is actually going to be not in a centralized location, but it's going to be in these distributed locations. So that the tsunami of data is not happening in the data center any longer, or even in the cloud. It's happening at the edge. And that leads us to this sort of planning model where we then say, wait a minute, we know data is growing roughly by the same rate by which we can compute it. which is, as you'll say, well, it's Moore's law, and Moore's law is slowing down, and Intel will say, no, Moore's law is not slowing down, and we keep going back and forth. It actually turns out that data is very persistently growing at 60% year over year, which means over 5 years, data 10x's, yeah? And that has to do with the fact that we can actually make sense of the data because we have more powerful computing. So that's not going to stop. But what is going to happen is the data is going to shift to the edge. So down here, you see here, just 10 years ago, right? Or now it's, I guess, 12 years ago. 12 years ago, we didn't care about the edge. It was like IoT early days, yeah? Very little data. Most of the data was in the data center or the cloud. But we're hitting this tipping point, which is not too far away, actually. And both Gartner and IDC are saying roughly by 2025, we're going to now see that moment where there's going to be given more and more data at the edge versus in any centralized location, inclusive of the cloud, which I thought was kind of fun when I plucked those numbers into my model here. I actually saw this little thing where my mouse is right now. That's what you might call that peak data center. Well, it's 2036, right? So it's far out there. But you know what, as this goes in this industry, this happens faster than we think, right? So now the kicker here is we're only 3 years away from the tipping point. So it's time to get after the edge. Yeah, why? Well, I said that a minute ago. When you're doing manufacturing, you actually, in this case, is actually a server manufacturer that we work with that's a subcontractor to HPE in Eastern Europe. And we make 45,000 servers every month, yeah? And you can see there's not a lot of time to do quality assurance here. We originally, and let me get my mouse here so you can see what the heck I'm talking about. So up here, you can see these cameras here. It's a little camera gantry. It's actually sort of like aluminum cross section here that's moving back and forth on a motor here. And why? Because we want to see all angles in the finished product so we can see if it's manufactured to spec, because each server can be customized, yeah? So what the customer has asked for, we want to make sure. Do we have the right RAM? Do we have the right CPU in there? Do we have the right number of CPUs in there? Are all the disk switches set right? If there aren't any, are the jumpers set right? Are all the connectors in place? And all this, we originally thought we could do with centralized cloud computing, but it took too long. We want to know inside a second, because the new next one is coming down the pike here. We want to know inside a second, is this a pass or a fail? So there was no other way to skin this cat but to take the compute and stick it next to where the scanners are. Now, why is this an important point? Because when you manufacture 45,000 servers a month in 5 parallel progressive assembly lines, saving 96 seconds on each server in assembly audit is a big deal. How big of a deal, you might ask? Well, it turns out that when I can actually process that data, which is 75 megabytes worth of data, instead of sending it across the wire to a central data center or cloud location, I can actually make sense of the data right there. These are data streams coming from cameras, high resolution, the whole bit, 75 megabytes, and the next second, another 75 megabytes. Well, if that's the case, I can save, like I said, 96 seconds on each server. You know what that adds up to? It adds up to a 33% additional capacity in the manufacturing plant. And that's precisely the kind of business outcome a line of business owner loves, right? What's that you say? By making my assembly smarter, by putting cameras at every step, you can all of a sudden make my expensive gear crank out more widgets? Yes. That's why people do it. That's the business reason why location matters. Because it's not just one manufacturing location, it's thousands of manufacturing locations placed close to their market. If you think about what Tesla is doing with the mega factories, right, or gigafactories actually, they're putting them in the big regions. Why? Well, Elon Musk said it. He said, well, it's easier for us to assemble to the market than to assemble in Fremont, California, and then ship the finished car on a boat. That costs a lot of money. So what we do instead is we manufacture to the local market by distributing the manufacturing capability. Aha, okay, got that. Now you start saying, well, we're a computer company, so why is this happening now? Why couldn't we have done this 20 years ago? And the answer really is, it has to do with density. Because not only is the data out there, but to make sense of the data, I actually have to go and get some compute distributed. Okay, so let's take a look. What did the data center look like in 2000? Not surprisingly, back then, it was 1 core per socket per rack U. Okay. And what is it looking like? Well, we already passed 384. We did that 2 years ago. And in 3 years, we'll be at 1292 cores per rack U. So what's the implication of this? The implication of this is you have tremendous dense computing. So instead of building your data center looking like this, and you can see here we have 1,292 servers around year 2000, 43 racks. Well, that's how Amazon started. That's how Google started. That's how scale out became a thing. Yeah, you had to write software to get all these little pizza boxes to work like a big mainframe. And you needed to locate that all in one place or to be meaningless. Well, get this, guys. You can actually now take this picture and shrink it down in just 3 years to what is essentially just enough that anyone can carry it to that edge location. So the miniaturization of compute now makes it possible to distribute the compute to where the data is. Okay, so you get this. So we're far beyond the data center, the center of the universe. Now our worldview is expanding into this. And incidentally, I was looking at some IDC data right before Christmas, and they came in and said 31% public cloud. And they're seeing a slowdown in public cloud, but they're also seeing a deprecation of the data center, but a huge growth, 16% year over year at the edge. So this is the world we're living in now. It's an edge first world. It's not a cloud first world or a data center first world. It's an edge first world. Okay, so that means we as a company have to do something together with NVIDIA and our partners, right? Intel, AMD, the like. So you look at that, you say, okay, the world now is there are clouds out there, which are big centralized constructs. Maybe you run your own data center and that's your cloud in Chicago, but you also have all the other locations that are worldwide. Okay, so you need to create essentially a global data fabric, a global mesh that will allow you to go from edges to cloud. Yes, so that you can see the center of the universe has shifted outside the cloud, in front of the cloud. It's now actually the ability to create this highly distributed infrastructure. And why is that? Well, because the data, as we talked about, is hot for just a second. The 75 megabyte example I just gave you, that data needs to be analyzed right there and then, inside a second, boom, and then we're on to the next server. So that data goes from high urgency, super hot. In other words, my chance of processing is super high inside a second. What happens after that? It falls to super low. So if you look at data lifecycle, right, that normally over in the data center, it used to look like this, right? So this is time, and this is probability of reuse here. So normally it would go like this, whoop, and you'll hit like 30 days in, you'll hit maybe a 10% chance of reuse. Over here in edge computing, it goes like this, bam, like that. It goes from super hot 1 minute or second to super cold the next. So we have no time to move data, like I just said. That means that now we're beginning to see the two bookends. There's the hot edge with the cold cloud as the backstop for archive and such. Okay, so now you get that. Well, what should we then do? Where should we start? Should we start in the cloud and move out? Well, wait a minute. If we already have workloads that have moved to the cloud, we don't need to move them out, right? They're not going to run better just because you put them at the edge. A new banking application for someone's smartphone is at human latency times, right? So we don't need to move that. That could clearly be in the cloud. But the kind of stuff we're talking about real-time analytics, AI, where we use GPU and such, well, here we actually need to look at the edge. So maybe it makes sense to not look at cloud first, but instead look at edge first. So if you look at edge first, you realize that an edge can actually run by itself. The cloud is not needed for the edge to run. Each of these locations are actually autonomous, just like an autonomous car. They can exchange data among themselves, such a thing as swarm learning, which we'll probably have a follow-up on later on this year. Swarm learning, right, basically says, yeah, I don't need some central location. But that also means that if I want to use a cloud or want to rent space at, let's say, an Azure instance or a Google instance or AWS, that means that's just another location in my distributed world. So this is an important thing to get. You start with the thing that is the most urgent. In other words, the least amount of latency that you can tolerate. And that's at the edge. Once that's squared away, everything is downhill. And that is actually an edge-in strategy. Now, I didn't come up with that. Gartner came up with that. But I wanted to make sure you understand the difference between edge-in and the notion of actually doing cloud out. We believe you've got to start with edge-in. So the intelligent edge has to be in place, and then you put a GreenLake superstructure on top of it as a platform, software, services, financial arrangements in terms of paying per use like you would in any cloud. But now this cloud is distributed. With AWS, Google, and Azure, it's just the back end. And your core data center, frankly, still lives on, but it's just another location. Okay, so we get that. So now comes the question, what is needed to build this distributed stack? Well, as you can imagine, you can't have distributed computing without networking. So we start with that. To that, we connect storage and compute. Typically, at the edge, we integrate the two. So it's an HCI-like construct where you have compute and storage in the same box. And then you need, of course, a data management layer. It both does the software-defined storage, but it also does versioning. It needs to know about other locations because we're no longer talking just one location. So we need to have this notion of a distributed data fabric that can understand data management in the distributed world. And why are we doing all this? This is all infrastructure, right? Because we want to run the workload out there. So we need to do some workload orchestration. And since we're running 34,000 coffee shops, it might be a good idea to do that from a central location and put some AI in. Yeah, now the stack is beginning to form up. But what? Wait, hold it. Did we forget something? Yes. What about this? The attack surface in a distributed model goes up exponentially. So you cannot have a security as an afterthought. It has to be embedded in the stack. And finally, because 34,000 stores worldwide or 1,000 machine shops or whatever it is you're trying to do, right? Could be burger joints, doesn't really matter. It's a distributed thing, 1,000 hospitals. We don't have the money, says the customer, to go and do this. We need help financing and running this. Well, then we deliver the whole darn thing as a service. So this is really a distributed cloud experience starting edge in. Okay, so have we done something? And this is really what we're talking about today. Yeah, the partnership between the two companies, NVIDIA, both with GPUs, right, inside the storage and compute nodes, right? Aruba for connectivity, both wireless and wireful and SD-WAN. And of course, the whole notion of the NVIDIA tool set, right? You have actually, and I'm not going to steal Will's thunder here. He'll get into that in much more detail. But it turns out that when we combine the two companies' efforts in a house stack, if you will, then you actually have AI at massive scale, where you can do inference at the edge, real time, where it matters. Okay, so how do we actually go to market? How do we actually engage? And of course, you might find yourself in financial services, healthcare, retail, media, entertainment, manufacturing, and so on, oil and gas, public sector. We have teams that speak your language. But the fun part is this platform as a service turns out to actually be a similar platform with some tweakings that then has a retail-specific application running to catch shoplifters, for example, or if it's financial services, it's a trading floor application using AI in real time, and on and on. Same thing with telco, manufacturing, and so on. So we begin to see this as a data center in a can with GPUs and software that allows you to do this. So now hopefully you have a good idea for why location matters, because you don't get time back. And therefore, we got to distribute compute. Yep.
Hey, Dennis, let me just chime in real quick. There's a question that came in here. There's a question just basically, do you have any guidance on when people actually should be thinking about moving towards this edge-in strategy? So is there a great example and a great architecture there, but is there any guidance about when people should be moving over?
Yep. Yeah, so the trick, and of course, mileage is going to vary from customer to customer. But let me say this before we get it to Will. The idea here is there are only really two things I care about to understand if I need to go through the trouble of edge computing. And that is, number one, how much data do I gather, right? Because if you use a gantry of cameras to do quality assurance, like I explained in the beginning of the presentation, we're talking hundreds of megabytes. And by the same token, the higher resolution the cameras are, the more defects I can catch. So it's in my interest to use the latest technology there with highest resolution. I can tell you we're at 200 megapixels already, and in just 3 years we're going to move to 356 megapixels. That's a tremendous amount of data. So the point I'm saying here is a good tip is if it's not just a little temperature sensor, but you're actually using streams of video, chances are you're going to be doing edge computing. If you're just going to have a little monitoring chip sitting, looking at the temperature in a freezer, you can probably do cloud computing because that's the other piece. The amount of data is the first part, and the window of opportunity by which you have to actually take action is the second part. So if you got a deal like one of our manufacturing companies we're helping said, we're dealing inside milliseconds now, okay? We're not only seconds, forget seconds, we're dealing inside milliseconds, and we got to make a decision inside milliseconds. Well, if you hear that, milliseconds, or even I would say sub-second or second, and with lots of data, edge computing is the choice.
Okay, awesome, thank you.
Okay, I'm going to give it to Will here, so I'll stop sharing. Are you ready, Will?
Yeah, thanks for setting the stage, Dennis. Great overview there. So I want to build on what Dennis is saying by talking about sort of three challenges that people face when going to these sorts of architectures. The first one is that the increasing data volumes we're seeing, that decreased time to urgency with data that we're generating and collecting and processing at the edge, require high performance and high throughput computing. Again, we don't have the luxury of sending these things off, processing them later, and thinking about them later. Everything is happening right now. Moving more processing to the edge means that we have a geographically distributed system. So as Dennis said, we need a single control plane to manage not only our applications that are running across many nodes, but applications that are running across many time zones. And since our node failures are costlier to resolve given geographic distribution, you might not have an IT staff in each retail store, for example. We'll want it designed to minimize failures. And the other consequence is that we don't have the luxury of amortizing the costs of excess capacity across our whole data center. Our edge tiers need to be able to handle surges in demand, or else we have to deal with dropping data. And the third challenge is one of people, right? Technology is super exciting. You know, we're all in this industry because we like technology to some extent, but technology is built, shaped, and deployed by humans. And technology is built for humans, right? It's serving human purposes. So we need to consider the teams who design, build, maintain, and depend on the systems that are processing our data and training our models to get us business value. So let's talk first about what high performance means in different contexts. Sometimes people think of performance as just a luxury, but it could be something as simple as processing the existing data set faster. It might mean doing the same amount of work with less complex or less expensive infrastructure. For example, doing things at the edge with fewer servers than we have in our entire legacy data center. It might mean solving more complex problems or solving existing problems more precisely. Maybe it means that we're meeting a tighter SLA or meeting an existing SLA more comfortably. Again, as Dennis mentioned, in a lot of these edge applications, the time between when you get the data and when you have to learn from it and act on it is very, very short. So this is an important benefit of high performance. It might also mean taking a query and turning it from coffee break latency to interactive latency, really improving the productivity of your analyst. So high performance can mean a lot of different things. And I hope it's clear that high performance is especially critical in this new edge context. But the challenge with high performance is when you think about high performance, you think about supercomputers. You think about people designing workloads to run on specialized hardware specifically. You think about someone who can make sure that they're utilizing thousands of processors or thousands of cores and synchronizing between a lot of fine-grained tasks carefully. Now, when we think about data scientists and data engineers and the people who build machine learning systems, we often talk about a Venn diagram of skills because these roles have evolved over the years. And maybe a data scientist knows a lot about statistics and a lot about software development and a lot about domain expertise. Maybe a data engineer knows about databases and high performance computing and parallel computing. But if we think about what these roles have in common, one thing that they all have in common is that they're not really focused on classical high performance computing techniques, right? A data engineer might focus on algorithms or, sort of systems knowledge, but they're not going to be the kind of person who's programming a supercomputer. That skill set is out here. So if we want to be able to have high performance hardware and let the teams who build these systems take advantage of it, we need to meet them where they are. So I want to take a quick detour and talk about who those teams are and what they do. If you're learning from data, you have a process that looks a lot like the conventional software development lifecycle. On the left-hand side, we have sort of deciding whether or not there's a problem to solve, getting all the data that we'll need together and making sure that it meets certain quality standards. And then in that middle section, we're going from raw data that's in a database table or in programming language objects or coming out of sensors or cameras and turning it into features, vectors of numbers that a machine learning model can classify or further process. And then we're identifying the right model to solve a problem. We're tuning the parameters of that model so it performs well, and we're validating that it performs well on data it hasn't seen, as well as on data it has seen. Once we get there, we're at the stage where we can start building a production system. And there are a lot of challenges of putting machine learning techniques into production systems that we only see in production. And that's why we have a lot of back edges in this graph. Just like with software development, you might realize after you put a technique into production that it doesn't totally meet the needs of your organization, and you need to go back and revisit some assumptions you made earlier. Now, because a lot of the tasks involved in model training and feature engineering and model validation and experiment management are numerically intensive and naturally parallel, a lot of people know that you can use hardware acceleration and GPU acceleration specifically to make deep learning in particular and machine learning techniques more generally faster. But really, to provide benefits for the systems that are processing vast quantities of data at the edge, we need to extend those benefits to the whole workflow and to the teams who are working together to build these systems. So I've sort of overlaid on this diagram a list of the personas who are involved in building these systems. We have data scientists who are really involved with finding patterns in data engineers who are involved with making data sources, structured and unstructured, at rest and in motion, available at scale and securely and with governance. We have business analysts who sort of focus on answering questions about data without training models, with queries and analytic processing. And then we have the developers, the ML ops engineers who put everything together into a system that can produce business value. So we really want a solution stack that meets these different audiences where they are and makes it possible for them to do their jobs. And that's some of the software that I want to talk about today. NVIDIA Rapids, NVIDIA Triton Inference Server, and the Rapids Accelerator for Apache Spark. Each of these frameworks takes a problem specific to some of these personas and provides a comfortable interface to accelerate these problems with NVIDIA GPUs. So if we talk about these different audiences, if we talk about data scientists, if we talk about data engineers, if we talk about ops teams, what environments are they comfortable with? Well, data scientists overwhelmingly work in popular environments like Pandas, which is a data frame processing library in Python, scikit-learn, which is a sort of Swiss Army knife for machine learning in Python, and other libraries in the Python data ecosystem. Data engineers, if they're working in a JVM context, Apache Spark is an extremely popular scale-out framework for data processing, ETL, structured query, and analytics. And ops engineers want to take want to have a microservice that they can put into production and monitor to integrate a model with the rest of the system. And that's where these pieces fit together. They provide accelerated implementations of these things. We'll see how it works now here. So the first thing I want to talk about is NVIDIA Rapids, which provides GPU accelerated implementations of interfaces that are familiar to data scientists who work in the Python data ecosystem. So the cuDF library provides a GPU accelerated data frame for structured data, data manipulation, data munging, right? Data cleaning. cuML provides accelerated machine learning, but the whole sort of inner loop of the data scientist workflow, from feature engineering to model validation and hyperparameter tuning. cuGraph provides a GPU accelerated framework for graph analytics. If you're dealing with graph problems, whether that's in social networks or anti-money laundering or any number of other use cases for graphs, you're going to benefit from acceleration there. These libraries all integrate with Dask, which is a scale-out framework that enables you to work on partitioned collections. So you can work, if you have one node that has a GPU, you can work on data sets that are too large to fit on that GPU by itself. If you have several nodes with GPUs, you can scale out across those nodes and distribute your problem to get a result more quickly. When we're talking about the data engineering component, well, these libraries also support those early stages in the workflow, and exploratory analysis is actually a really important use case for acceleration, because if you're thinking about taking a data set that has millions of rows and tens of thousands of features and trying to see if there's any structure in it, you're going to want to project that onto something that you can plot and look at and understand. I find it a lot easier to understand 2 dimensions than 10,000, right? So I think that's a really important use case, and we've seen cases where visualizing a complex data set goes from taking half an hour or 45 minutes to seconds. You literally don't have to leave your desk while it's computing. Finally, in the ops side of the coin, we're looking at accelerating that machine learning inference and having integrations with popular deep learning and machine learning libraries. So TensorFlow and PyTorch on the deep learning side, XGBoost on the tree ensemble side, those are all accelerated by GPUs. And those models can all be accelerated in the Triton Inference Server, which is a service that you can deploy that knows how to turn models into prediction services, basically. So Rapids is great for the data scientists who are working in the Python ecosystem, but a lot of work in our data processing systems runs in the JVM, in sort of the ecosystem that built out of the big data ecosystem of 10 years ago. And a really popular framework in that space is Apache Spark. Apache Spark has sort of a general purpose distributed scheduler, distributed collections on top of that scheduler, and a number of high-level interfaces to make it easier to solve real problems rather than just writing directly to a distributed data structure. So the ones I want to focus on are Spark SQL, which is a library for structured query and data frame processing and ETL, and the Spark scheduler itself. With these libraries, we've actually developed the Rapids accelerator for Apache Spark and NVIDIA, which builds on that low-level data frame support in Rapids and takes Spark query plans. So whenever you run a database query in a database or in Spark, the database translates your query into a plan of what it's going to do, a very low-level plan. The Rapids accelerator for Apache Spark plugs into Spark Query Planner and replaces those plans, replaces those graphs of fine-grained tasks with tasks that run on the GPU where possible and appropriate. So you're able to get that speed up without changing your Spark applications at all in the case of the Rapids accelerator for Apache Spark. Now, transparent acceleration comes with some trade-offs. You can't guarantee that a job that accelerates transparently is going to accelerate as well as a job that's written directly for an accelerated framework. So we can sort of look at the trade-offs that users see. If they're running an Apache Spark job, they can get really good benefits just from installing the Rapids accelerator for Apache Spark on their data frame jobs. A lot of times there are some operations in a query plan that can't accelerate well on the GPU because they were designed for row at a time processing on CPUs. And by working around some of those minor changes, we can see much greater speedups. Finally, if we're able to code parts of our application directly to Rapids, in some cases, we can see much greater speedups because you're targeting a GPU native framework directly. And then finally, in the upper right-hand corner of this, if you have an HPC developer who wants to get really close to the hardware, obviously you're going to get the best speed up there, but it may not make the most business sense for you to choose that option versus using one of these more comfortable frameworks. So we've seen a lot of really awesome successes in industry with accelerated machine learning, but a lot of things that I've seen in the last sort of 10 years of thinking about big data and thinking about machine learning is you have a lot of practitioners who had to become infrastructure experts, right? 10 years ago, you had someone who was a data scientist, someone with a PhD in economics who also happened to know how to spin up a Hadoop cluster in the public cloud, right? I don't know that that's what anyone really wants to, what any data scientist really wants to do. You want this to be something that your IT department can manage and support, something that can scale to your enterprise. And so NVIDIA EGX, the NVIDIA EGX program is a program we have where we work with vendors, we work with HPE, and we sort of have systems that we sort of say, if you're going to be doing these kinds of accelerated computing tasks in your data center or at the edge, we know how to get you started. And an important component of that is NVIDIA certified systems. NVIDIA certified systems take the guesswork out of saying what accelerated hardware, what GPUs, should I put in this system to get the best benefits out of it. These are systems that we've worked with HPE to pass certification tests to validate individual configurations for performance, manageability, security, and scalability. And because we've done that, you don't have to guess. You can say, I can use the same servers that I'm comfortable with using. I'm just going to find the NVIDIA certified configuration of those servers. So let's look at Denis's stack from earlier and see how it shakes out with this accelerated software integrated into it. The bottom layer, we have the accelerated hardware, right? We have those NVIDIA certified systems from HPE. Then we have the Ezmeral Data Fabric management layer and analytics services. And on the top, we have the NVIDIA Rapids library and the Rapids accelerator for Apache Spark, which NVIDIA and HPE have worked together to validate work really well together. So you're able to scale these problems out to the edge without telling your data scientists that they have to become HPC developers. You're able to do more with less without taking on management challenges because this stack is addressing those for you. I'm going to turn it back over to Denis now, who has a case study.
Hey, Will, before we go over, thank you very much for that those details. There were a couple questions that came in when you were chatting. I'm just trying to chime in here at the end here. One of the questions that you just mentioned, right, we've done some validations of the stack. What sort of performance speed up would people expect to see? Or maybe you could talk to a little bit what types of workloads are most applicable here for bringing the GPUs and the software and infrastructure together.
Yeah, for sure. So I think I want to preface this with a little bit of level setting. One thing that a lot of data scientists do, no matter what in hardware they're running on, is think in terms of running on things a collection at a time versus an element at a time. So for those of you on the call who aren't familiar with data science frameworks, a really popular numeric framework in Python is called NumPy, and it provides sort of an array programming interface. Now, if you wanted to say, I want to double every element in an array, you might think, oh, I'll just use a for loop, right? Operating one element at a time. Now, NumPy actually enables you to operate a collection at a time and say, I'm going to multiply this array by 2. And that happens sort of in the library, and it happens much faster. So I mention this just as an analogy because a lot of times the things that will accelerate really well on the GPU are things where you can think about an operation that logically executes a collection at a time. And this is no different from running NumPy on the CPU or Apache Spark on the CPU. The difference is that because GPUs are much faster than CPUs, the difference between running some operation serially and running it in parallel will be a lot more obvious. So the kinds of workloads that we see accelerate really well, again, visualization is fantastic. Model training is fantastic. On the Spark side, I think complicated analytics, if you have to do a data cube, if you need to drill down and sort of try and identify a pattern in multidimensional data, that's going to work really well. Windowed aggregates will accelerate really well. And complex joins, especially where you have really high cardinality relations, are going to accelerate really well as well. But there are a lot of case studies. We could point you to if you look at developer.nvidia.com. There are a lot of sort of success stories with these frameworks to drill down on more.
Okay, and there was one other question that came up just specifically. You were calling out Python and Spark for the Rapids accelerator. Does Rapids also help accelerate some of the other frameworks like a PyTorch or a Caffe?
So it's integrated with PyTorch. There's an interface basically to say I want to prepare data with Rapids, leave that data on the GPU, and then operate on it directly with the deep learning framework. It's called the Array interface. A lot of frameworks support that.
Okay, so it expands out a little further. Perfect.
Yeah.
We'll appreciate that. So I think we're going to move over here just to Denis, maybe drilling into a current joint customer that we have, and just kind of showing this better together of our systems, our software, our validations, and our integrations kind of coming together. So software, hardware, and services coming together in a real customer example. So Denis, back over to you.
Yeah, appreciate it. Yeah, so you can see there are a lot of moving parts here, and it can be very easy for you to fall into the trap of my head is splitting open, it's too much complexity. So I like to take this example, which is a real example where NVIDIA, together with HPE, has actually worked with a very large healthcare provider that operates across 140 countries worldwide. And they have thousands, hundreds of thousands of pieces of equipment. And what they're engaged in actually making super persons or super people out of the doctor by giving them interactive AI for purpose of X-ray and MRI diagnosis. So that there's a good example of how machine learning and inference in a distributed world is actually saving lives. So let me show you how that works. And I like to give you this example because it helps you understand that you can break down this complexity into repeatable, location-oriented templates. Yeah. So let's take a look. What's the first thing? I'll use this example here. It could be a manufacturing plant, a coffee shop, a burger joint. It can be anything. But in this case, it's a hospital or clinic location. Here we have, of course, as I mentioned, doctors that want to use cameras with a data stream into some sort of compute. And all this is on a little cart. So it's wireless. So here we have a classic example of we have to have some Aruba wirelessness here, and we have to have some compute and cameras tightly integrated with some sort of inference engine for that doctor to do her job or his job. Same thing here, same thing here. So what's the first thing you see? Oh, if I solve this little data problem here, I can just replicate like a cookie cutter. Like how many doctor instances do we need for this particular solution? Let's say it's 100 in a hospital. Great, it's the same recipe done 100 times. So what you then need is the ability to manage that fleet inside the hospital from a central location. And this is again where we put in a little wine closet, we put some servers, and we're running a little data lake that's a distributed data lake in that actual hospital location. And then, like we said, networking matters. There's an uplink to the core of the cloud. Okay, so we got this, that we can treat the location as a confined set of problems with a one-to-many relationship all the way out to the very activity where that's taking place. Okay, good. So now you start saying, okay, well, what's the next step up? What if I'm having 140 countries worldwide and thousands of hospitals? You got it. You see the same exact one-to-many relationship. So like this was a little data world, if you will, little location. Well, there's multiple of these locations and they're scaling, right? So you have to have, again, a central location. So there's a one-to-many here, one-to-many, and there was a one-to-many inside the location here, one-to-many, yeah? So you have essentially a tree structure that starts from a central location and then spans out. So where does cloud fit in? Well, it actually turns out that it fits in here. So I want to show you real quick how this actually works and how the combined stack is solving the problem. So here we have a classic case of cameras, right? We got rid of the doctors here. So this can be anything. It can be quality assurance. What did we put in here? We put in NVIDIA Jetsons, which are these little almost lunch-size boxes that can do inference and direct camera streams, yeah? And then we put a cluster here, an HPE cluster, and now the locations taken care of. Like I said, replicate that across the locations. So that gives us an edge stack, Aruba networking, NVIDIA Jetson and GPUs, right? We have GPUs in here too, right? And it turns out the Ezmeral Data Fabric, like Will talked about, and the Ezmeral runtime. So here we have a combination of hardware, software from both companies. Okay, now what happens from a learning perspective. Because what we really want to do is run machine learning here and then push out to the locations here the actual new inference patterns by way of a new neural network so they can recognize even more cancer clusters. But we also want to learn from what the doctors are seeing out here, and we're sending that back. So if I was to pick another color here, just to illustrate, there's a virtual search cycle that goes like this, yeah? Data gets published, data gets harvested, data gets published, data gets harvested. And it's very similar to the way Tesla is actually learning from everyone who has a Tesla, and then they're training their whole fleet. So this is known as federated learning, where you have a central location, in this case, the data center run by this healthcare provider that then uses all the information available across the edge to do a better job across all edges. But the decision loop that the doctor is taking care of is happening out here, but he's benefiting from all the other doctors are seeing. Now, does that mean we don't use the public cloud? No, we can extend the data fabric to the public cloud too, and then we can move data up there for backup purposes and for archive, things like that, right? Things that we go, oh, you know what? If that hospital got hit by a flood where we have the main data center, we actually would like to have a other copy of the patient's data and all our training information. So this is a classic edge to core to cloud model with a virtuous cycle running of inference at the edge and machine learning in the center. Any thoughts there, Will, real quick? I know we're sort of wrapping up on time. Is he on mute? Okay.
No, I one thing that comes to mind, Dennis, is just that, I think when we're talking about devices, right? If you're talking about a car, right? If your car is a new data center in the edge computing world,
yes,
that maintenance burden, that needing to have simple, manageable infrastructure becomes even more important, right?
Absolutely.
Than it does in a retail store. So
yeah, absolutely, and you can argue, like we talked about earlier, the more complex the data sets at the edge, the more critical it is. I mean, you can't say, oh, I'm sorry, your grandfather died at the operating table because AWS was down, right? So you're picking up a great point, which I think we can learn a lot from autonomous cars. Each hospital location has to be autonomous, has to be able to run on its own, but it benefits from the fleet learning of the entire sort of family of similar hospitals doing similar things. So you're right. And then the question you're poking at is, what if the hospital says, well, we want to heal patients, but we don't want to manage this? Well, that's exactly where HPE's GreenLake comes in, and you can manage this whole thing through a dashboard, and it hides all the complexity for the DevOps folks who just want to deploy new learning modalities and new neural networks and whatnot, new containers, if that's what they want to do, right? It's a containerized workload here. So it could be VMs as well. Let's not get sucked into the detail. But the point really is, we have a distributed world. We can go to a central location. We can use GreenLake Central to orchestrate what's happening. We can publish new things, and the whole life cycle can happen. And all the complexity is managed entirely by HPE and GreenLake. Great. So that was it for us. I would say if there's a couple of little sort of takeaways, ask yourself these questions. These are good questions to start thinking about edge in. What can be done better when local decisions can be made in real time? Like, for example, we use self-driving cars. The only reason you have self-driving cars, I even want to care about it, is that your self-driving car can run more safely than a human-driven car. And if we're not at that point yet, we probably don't need to cut over. So ask yourself the question, are there things I can do better if I did it in locally, location matters, and in real time? And also, what should I start with? Because I want to start with just one location, and I want to scale out, right? So let's start in one location, do a pilot, and once that delivers the goods, then we have this beautiful multiplication effect. I like to say, if you save $1,000 across 1,000 sites, guess what that is? That is actually $1 million, right? So it adds up quickly. So there's an economic outcome, like we just talked about, and GreenLake is here to help you scale that. So all we're saying is select HPE and NVIDIA for your next project. So with that, thank you so much for your kind attention. And it was great to be with you today. I think we had like more than 100 folks on. So That is phenomenal. Good way to start the new year.
Great. Dennis and Will, really want to say thank you to both of you. And again, I think we really highlighted going through here and just kind of recapping the shift to the edge and that the technology and the data and the intelligence is moving out to the edge based on the time to value that you need and that hot data and actually getting those insights. We saw some examples around optimizing your factory, self-driving cars, as well as an example around improving personalized medicine. And I think really what brought this together is that full end-to-end. This requires looking for a partner who has the hardware, the software, and the services expertise to actually deliver this as a full end-to-end solution. So again, Will, thank you for joining us. Dennis, thank you. And Didier, thanks for hosting us on the Munch and Learn series. Didier, did you want to close with anything else?
Yeah, I just put up the end of session poll. Thank you very much for answering that. I would like to, on behalf of the HPE Dev community, thanks for our 3 speakers here. That was a super interesting talk, and I think we had a good crowd. So thanks a lot, and I'll talk to you on our next Munch and Learn. Thank you very much.